Okay, what I'd like to talk about then, we've been talking about models, philosophies, and stuff. We're going to soon start to get into the machine learning where you really talk about building them. Um, but before this, I'd like to spend a session on just evaluating. Um, how do you tell whether a model is, is good or not? Okay, and there are. Um, again, there's a standard set of statistics that are involved in trying to regulate, to judge how good a classification model is or a regression model. Again, most machine learning models reduce to either being a classification problem where you're given examples and you have to produce a label from it from some kind of a finite set, or a regression problem where you're given an example, okay, and your goal is to produce some kind of a numerical prediction. So for the movie gross thing, obviously that was a what you call it, a that would be a regression problem. If you wanted to determine what genre a movie was, that would be a classification problem. And there are different test statistics that we use on these things, but there's also different what I would say there's kind of a procedures for reliably doing testing, and I think I'd like to make sure that we understand that today before we get onto the projects and the machine learning. But okay, so let's start off with how do you judge if a classifier is doing a reasonable thing? Okay, a classifier is, in classifications, um, typically, the simplest and probably most common form of classifiers are binary classifiers, where you're going to be determining whether something is labeled as being in a, there's two different kinds of classes. Maybe it's spam and good, maybe it's healthy or diseased, maybe it's binary classification. And the when we run a binary classifier on a two labeled set of things, we get kind of four possible things can happen. Okay, if our elements are can be either a members of a the positive class or the negative class. Um, and we can either predict positive or negative for each element. Okay. The true positives are when it's in the positive class. Typically, we call, when we have a binary classifier, we call one of them the positive class and one the negative class. The positive class is typically the one that we are more interested in, typically the smaller of the two classes if they are equal. So like if you have a disease versus healthy, typically positive would be representing the disease. And then kind of four possible outcomes. Basically, two when we get it right and two when we get it wrong. A true positive is when we guess positive and it actually is positive. A That we get right. A true negative is when we guess that it's negative and we get it right. Those are the ones we get it right. When we get things wrong, we can have false positives and false negatives. A false positive is when we say it's positive, okay, but it really is negative. And a false negative is when we say it's negative, okay, but we say a false negative is when it is positive and we say it's negative. Have I been consistent there? I always get confused with this. So let's just go and do this one more time. A false positive, okay, is something where we say that it's positive, okay, but it really isn't. A false positive, I guess, is the guy who we tell that has cancer when they really didn't. okay? And a false negative is the guy who we said was healthy when they really had cancer, okay? Any questions about that? So on any binary classification problem, any binary classifier, when we do a labeling, our results are going to fall into one of these four bins. Any questions about it? Now, one way to think about this that I think is a interesting class of classifiers, and actually we'll see later on, are what I would call threshold classifiers. Suppose we had a score that was going to be related to kind of positiveness or negativeness. Let's say you had a score that measured something about how likely a a sample had cancer, okay? Or maybe a score that is more like that the higher the score, the more likely it is cancer. When you have a function that basically is going to give you such a score, to turn that function into a classifier, you need to be able to set a threshold. It should be clear that if we have, in this particular example, we have some kind of a score, okay? If we do the distribution of all the positive examples, which are the ones in blue, the real positive examples, okay, that's their distribution. We also have a distribution of the negative examples. That these distributions are different according to our score means that the score can help classify and make a decision as to whether a example is positive or negative. Okay, you know, the fact that these things overlap means that if we're going to try to make a decision on that score, we're doomed to making errors. Okay, what is the right place to make the the decision here? It should be clear that wherever we draw a line, okay, we would have a classifier that would say that everything on this side is positive and everything on this side is negative. It's going to get some things right, it's going to get some things wrong. What is the right place to set that threshold? Does everybody kind of see what the problem is? You have a score or a statistic that's capable of, providing insight into the class. Where would you draw, if you have to draw a line, where do you draw the line?
It depends on what's more acceptable, false positives or false negatives.
It should be clear that the answer is it depends. That's exactly right. Okay, that it depends what you are actually concerned about. Okay, let's say that this was a cancer diagnosis. Okay, that we want to know, or let's say COVID these days. You always use cancer. Let's say with COVID, where did we? And let's say the positive things were the people with COVID. The negative ones were the ones that did not have COVID. Where should we draw the line? Does anybody have an opinion on this? Again, you're going to have to tell the patient either they got it or they don't. Where do you draw the line?
Probably to more prohibitive of false negatives.
You are concerned about false negatives. So let's just think about it. If we draw a line, again, we've got true positives are the ones we have told that they got COVID and we were right. False positives were the people we told had COVID and didn't. Right?
Yeah.
False negatives are the ones that that have COVID but are now free to infect the world because they were told that they didn't have it. And true negatives are the ones that were didn't have didn't have it and were told that they didn't have it. So where did you say you wanted to draw the line?
So to the left of the black.
To the left. Your instinct might be to draw the line someplace like here. If you
Yeah.
draw the line here, what you call it? The good thing is there's relatively few people who are going to have the disease, who, you let off. The bad thing is, of course, that there's going to be a bunch of people who didn't have the disease, who are going to get scared. Okay? So what should be clear is that these kind of threshold classifiers are important things. Okay? And that, when we look at logistic regression ultimately will reduce to building a threshold classifier. Most techniques will ultimately reduce to that on some level. Okay? Where is the right place depends upon how we feel about false positives versus false negatives. Any questions? Anybody, just for the purposes of having a discussion, can anybody think of a reason why you might, in a positive, an example of a label of a positive thing, you might want to err on just identifying the people who really, really have it? I don't know if there's any use case you can think of where this is the right separator.
I know with some oncology testing, they prefer that because they would rather not proceed with chemotherapy or other radiology treatments if you definitely don't have it.
Right, so you can imagine certain kinds of, okay, so I'm now saying in oncology, if you had a world where the treatment was very, was produced horrible effects like chemotherapy does, and if the benefits were relatively limited, if it was a cancer that was hard to treat, okay, and not too many people do very well with it, you might want to err very much on making sure that you identify people who really, really have it. Okay? Any questions? I was thinking, just if you're thinking about someone you want to mug, okay, there's rich people and poor people. Okay? There are a lot of people out there who are, rich, a lot of people are poor. You want to make sure that the one that you rob is one of the rich ones. Okay, there's a lot of people out there you're not going to rob. Okay, it might be you want, the standard to be very good. I think the chemotherapy example is better than that. But okay, does everybody kind of get that idea? Okay. That said, having the right evaluation metric helps us make this kind of a judgment. Okay. Any questions? So what statistics can we use to measure how good a classifier is? The most obvious one is accuracy. Okay, and accuracy is basically the number of right answers over the total number of guesses. The right answers are the true positives and the true negatives. The total number of answers is over here. Okay, the accuracy is then this ratio here. Now, is accuracy a good statistic? Okay, and the answer with everything is, of course, it depends. Okay, now in a binary classifier, I find that I usually, when I think about trying to understand a evaluation metric, I usually like to think in terms of the monkey. Okay, what is it that the dumbest classifier you can build, or a random guesser, and how would they do on this? Okay. Suppose a monkey were to guess positive or negative by flipping a coin. What would be the accuracy of the monkey? Okay. The interesting thing is the monkey will get an accuracy of 50%. Okay, if they guess with a 0.5 chance. Okay, does everybody kind of see that? It's a little bit, that may not be obvious. What if they were only 10% positive and 90% negative? Okay, what would the monkey do? Actually, let's just think if it is that way of doing it. Okay, certainly, I guess if it's zero, I find it a little. Let's work through this. Certainly, if it was 0% positive and 100% negative, what would be the answer here? The true positives would be 0. The true negatives would be the 50% of negatives that we got. Okay, and so we would end up with, again, 50% right, okay, on that. What if it was skewed, but not 0? Okay, do we necessarily get a accurate, what accuracy would we get? Okay, the true positives, okay, there would be a probability of P of the thing being positive, and we would get that right. How often? Okay, of the true positives, we would get basically half the true positives right. Okay, I mean, of the positives, we would expect to get about half the positives would be true positives if we were guessing equally half and half. Of the negatives, okay, we would expect to get about half the negatives. Okay, because so the true negatives would be about half of that. Our total here would be this over the total number of positives plus the total number of negatives. Does everybody see that even if the probability of a class being small, okay, was okay, I'm getting a little fumpered here. But do people agree with me that regardless of how even or odd the split was, accuracy of the monkey would be about 0.5? Okay, any questions? Now, that's not necessarily the best dumb answer, okay? If you know that one class is bigger than the other class, let's say we did know that 90% of the things were negative, we would always be better off picking the bigger class, okay? And that we would get an accuracy proportional to the probability, the frequency of the biggest class. Any questions about that? Okay, so accuracy is a reasonable measure. But actually, what you call it, when the number of positives is very, very small relative to the accuracy of the number of negatives, okay, accuracy doesn't turn out to be a very good measure. Let's say that only 5% of the tests, okay, are actually cancerous. Okay, our monkey would have an accuracy of 50%. Okay, whereas in some sense it's telling you nothing about whether or not people have the disease or not. Does everybody kind of see? If I had a class where I just randomly guessed, getting an accuracy of 50% sounds good, but if one of the classes is much smaller than the other, okay, this is a pretty meaningless number. The precision is kind of what we want on a medical test, is a high precision. Okay, what is the high precision? The high precision says that basically, what's the number of true positives over all the actual positives? Okay, so true positives means we said cancer, and it was cancer. Okay. True positive, false positives, and I always get this confused, were ones that were, okay, which is false positives again? Somebody yell this out because I always get confused.
I
It's
find
not
that
cancer,
when-
but we
yeah.
labeled it cancer.
Yeah,
What was that?
it's like telling a man they're pregnant.
A false positive is telling a man that they're pregnant, okay? So let's go back here. False positive, sorry about that. Let's go back to this again. I always find these confusing. A false positive is when there was a negative example labeled positive. So that would be again, somebody who wasn't pregnant named labeled pregnant, which is what I think we're talking about here, or a guy without cancer that was labeled with cancer. So what does precision tell me? It says that out of all the people who we're saying are positive, what fraction of them really were positive, okay? And, in the case of the monkey, okay, we would only get 5% precision, because the total number of true positives we get in the case of the monkey would be the positives over 2, okay? Positives over 2, the others would be the negatives over 2, okay? And this would be a very, very high number, okay? So the precision is saying when you get a positive, okay, how confident are we that it really is a positive? Any question? Okay.
Yes. Hello.
Yeah.
So sometimes we have to deal with class imbalances. Is it more important to ensure the precision and accuracy metrics is valid?
Okay, so class imbalances are an important problem. That's exactly what I guess we're having when we say that the number of positives is less than the number of negatives. Okay, sometimes the class imbalance is because there just is an inherent imbalance in the universe. In the case of cancer, hopefully most people don't have cancer. Okay, and so we are often faced with a world where there is an inherent class imbalance. It doesn't mean that, we want to be accurate when we say that something is positive. Okay. And so being aware that class imbalance kind of messes up these statistics is an important thing to understand.
Is it more important to fix the imbalance in training data or test data or both?
So there then is a question of what do you do about the world in a world of imbalance when you're building a classifier? Now, in an ideal world, okay, as we will see, we will talk a little bit at some point about how you deal with imbalanced data. In an ideal world, you would have as many positive examples as many negative examples, and that it would be equal and for training a classifier. But often it's hard to find positive examples. And there are different ideas, things of what you could do with that. One possibility might be throw out enough negative examples so that you have the same number of positives and negatives, because certain classification methods do better with that. But of course, it seems bad to throw out negative, data that could have been useful to train it. Sometimes you weigh the positive examples more. If you have twice as many negative examples as positive examples, anytime you get a positive example right, you get 2 points instead of 1 point. Okay, so it depends upon what your situation is. Ideally, we would have equal numbers of both, but ideally we would all be handsome and rich. Okay, and that's not necessarily the case. Any questions? So recall, okay, is a question of that we're willing to let scare some people, so long as we identify most of the people that really have the disease. Okay, so true positives over false negatives. A false negative is somebody who had cancer but didn't. We said no, correct? Okay. And this says that of all the people that had cancer, how many of them, what fraction of them were we able to identify with these tests? It should be clear that in the cancer case, we want a high recall because we don't want to make mistakes. Okay? But can anybody give me a classifier that has perfect recall? A technique for building a classifier that has perfect recall? What about one that always
Just label
says
everything
everybody has
positive?
cancer? If you always say positive, okay, then basically your recall is going to be perfect, right? It doesn't make it necessarily a good classifier. But it is clear that we would like a high recall in many situations. And the recall is the number, the fraction of the positive cases that we were able to classify. Does everybody kind of see this? We would like a high recall. We would like a high accuracy, okay? We'd like a high precision, okay? But the different classifiers will do different things, okay? Any questions about that? Any questions? The F-score is a way of combining this idea of recall and precision, okay, into one statistic, okay. The recall basically again said when we say true, how what fraction of the truths did we capture? The precision says when we said true, how accurate were we when we said true? Okay. If you said true once, okay, and you were right and said no for everybody else, that would give you a perfect precision, but a very, very low recall. So if you have a classifier that is going to make call only the easy calls, it should score a high precision, but a low recall, okay? The F index, okay, the F score is basically the harmonic mean of the precision and the recall, okay? And this enables us to this statistic kind of captures a balance between saying yes when we're confident and getting a lot of the yeses, okay? Any questions? One interesting consequence is that the precision, the F score as we've taken it here, is the harmonic mean of the precision and the recall. That's less than the arithmetic mean. So it basically it's hard to get a high F score, okay? And so the F score is kind of a good single statistic that captures how well your classifier is doing. Any questions about that? Okay, so I would say F score is the, if I need one measure, okay, to judge what I'm doing, I would typically use the F score, okay? But it's interesting to see the suite of different statistics, okay? Again, accuracy is, I find, easy to interpret if I have a binary classification problem with equal class sizes. Accuracy then kind of makes sense. But when you have unbalanced class sizes, okay, it's it tends to be misleading. And getting a high precision is very, very hard when you have a very small number of positives. Why is it hard to catch terrorists? Does anybody have a theory as to why it is difficult to identify terrorists in the population? You build a classifier to identify who's going to be a terrorist.
There's very few of them, and most of the things they do are also things that everybody else does.
Yeah, so that's basically it. If there's a very few terrorists, it's very, very hard to be accurate on just that very, very small class. Okay, and like I say, the F score is a good way of combining, understanding what understanding what these issues is and giving you a statistic that combines them. Any questions? There is one other statistic that I really like and have slowly been, and it has been warming on me recently, for judging these kind of threshold classifiers, which gets at the idea that there's many different places where you could draw a cutoff. Okay, an ROC curve is a receiver operator curve. This is from some old radar terminology, so it's kind of a weird name. But basically, let's think what happens if we have a, in this case, we want to identify, again, separate positives from negatives. Let's think about all and on this particular example, my positives are on the right. Okay, usually they're somehow on the left, but so don't get too confused with this. But let's imagine what happens if I slide my decision boundary over to the slowly over to the left. Okay, if I've done a reasonable job here, my early calls are going to be the most positive examples I can find, the things I'm most confident about. Okay, and let's now think that as we slide our threshold classifier, slide that threshold over to the left, each time we move it, it's going to step over another example and make a classification. Actually, as we move the classifier, the threshold over to the left, it's going to be taking certain things that were labeled negative and now kind of label them positive. Okay, that's kind of the result of shifting this boundary over to the left. Okay, what an ROC curve is going to do is measure the true positive rate over the false positive rate. Okay, as a as a function of where we put the classifiers. Okay, so suppose I put my threshold over here and say that on everything on this side was positive and everything on this side was negative. What would that situation correspond to? What would be my true positive rate? What fraction of true positives did I have over all the positives? Okay, everything that was positive got labeled positive, and so my true positive rate would be 0. What would be my false positive rate? Okay, what fraction of false positives would I have if I had my my threshold all the way to the left? All the negatives would get classified as positive, and my false positive rate would also be 0, would also be 100%. If I had my classifier over here, let's say just after that first example, I correctly classified 1 out of if I look at how many decisions are made when I move my classifier right over here, okay, I will have made my first example would have been positive, and I called it positive. That's kind of a step when I cross an example. If I get a positive example right, that is a step in this direction. Okay. As I move my threshold over, my threshold over, I'm going to be calling more and more things positive. And everything I now call positive represents a step up. Every time I have a negative example that I call positive, that represents a step to the right. It should be clear if I explained it right, and I'm feeling like I'm talking too much and not quite saying it, okay? It should be clear that as I slide this thing over, originally, nothing got classified as positive. So my true positive rate was 0. I classified none of the positive examples as positive. I classified none of the negative examples as negative, okay? None of the negative examples as positive. When I slide this thing over, as I cross one of these things, if I cross a positive, that represents a step in the positive direction. If I cross a negative example, that represents a a step in the false positive direction, because I'm saying that everything to the right of this threshold is positive, okay? And so it should be clear, if you understood what I said, that kind of a threshold classifier describes a curve where it starts out at 0, 0, true positive rate is 0, false positive rate is 0. It ends up having declared all the positives positive and the negatives also positive. So it's true positive rate and false positive rate both 1. And as we slide, every time we slide it over, for every thing that we now get right, we go up. Every one we get wrong, we go to the right. And so we have a curve that ideally looks something like this, okay? If we were kind of just guessing, if we had these items in a completely random order, okay, every time we slide it over, we're equally likely to get it right as we are to get it wrong, okay? And we would expect that the curve should kind of be this thing on the main diagonal. But if we had a good classifier, the first things, the rightmost things, are the true positive examples that we think we're most confident with. Those we should be getting right. So we would expect that the first bunch of things we do, we're going to be getting it right. And then with time, we're going to get more and more wrong as the examples get harder, okay? And the curve is going to bend. So it should be clear, it starts here, it ends there. It should be clear that if it's good, it should stay above this 50% line, this diagonal, okay? And the shape of this curve does a lot of things for us. Okay, hold on. One thing it does is give us a measure of accuracy, of performance, because the area under this curve, okay, is going to be higher with a better classifier. What is the performance of the ROC curve? The best possible ROC curve we could get. Does anybody have a vision of what, if we had distributions, what distributions would give us the best possible ROC curve?
Is it when you fill the entire box?
When you fill the entire box, suppose, let's say we had a world where our scores gave all the positive things here and the negative things here. What is going to happen as we slide our classifier over? We say, I got it right, positive, 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 positive. When we got to this point here, we would have successfully classified all the things as positive with no false negatives. Does everybody kind of see that? And then as we keep sliding this thing over, we're going to start to accumulate false negatives. The best possible ROC curve would essentially fill this box. And the area of this ROC curve would be 1 by 1. The area under the curve would be 1. If we had a random classifier that did nothing, okay, interesting, that just randomly basically had these things, the scoring function basically had them in some kind of completely scrambled order. The area under the curve would be, you know, it's a triangle. That's half the area. That's 1/2. In general, a decent classifier like this one is going to have an area under the curve of greater than 1/2, but less than 1. Okay? And this gives us another statistic to kind of govern how well our classifier is doing. Any question about it? Any questions about what the ROC curve is or what the area under the curve is? One thing that makes an ROC curve nice is it actually, in a world where you have a sense of false positive, the value of false positives and false negatives, what's kind of interesting is every point on this, what you call it, every, kind of point on this ROC curve describes a classifier, which is going to offer a different trade-off of false positives and, false positives and other things. Okay. So if we look at something like this, if we took a look at a point on the ROC curve like this, okay, here we are a point where, what does this point kind of say? If we do the threshold where this thing was, it says, okay, our true positive rate was about 0.6. That meant that if we did this, we'd report about 60% of the positives correctly. Our false positive rate is quite low. Okay, it looks like it's something like 0.03 or 4 or something like that. Okay. But on the other hand, there's a lot of negatives potentially. I mean, there's still this 40% of positives that we're going to call negatives. Okay. And each point here represents a particular classifier with a particular trade-off. And depending upon how you value false positives to false negatives, you can pick any one of these points as being the one that you use. Any questions? So the ROC curve is good because the area under it gives you one statistic that kind of governs your whole trade-offs of how robust your classifier is, okay? And it gives you a bunch of choices depending upon how you value false positives or false negatives. Any questions? Now, we were talking about evaluating binary, binary classifiers in a world where there were just two labels, positive and negative. In general, classification gets harder when when you have more classes. Okay, if you have 10 classes, a monkey that's just going to be guessing the class is only going to get an accuracy of 10% instead of 50%. How can you evaluate meaningfully a multi-class classification system? One tool that I think is very, very useful is the confusion matrix, where here you have the actual answers. This was sort of some OCR thing where there's digits, okay? This was the actual letter, and this is what your system called, okay? This tells you how often did you say, in this case, how often did you say 3 when the number was a 5? Ideally, most of your examples would be on the main diagonal of this thing, okay? Because the correct predictions are on the main diagonal. But what else is useful with one of these multi-class systems? Why do we want to see the where we made? It's useful when we have this confusion matrix to show us where are the things where we're making mistakes. It seemed clear the system had a hard time. A lot of 5s, a surprisingly large number of 5s got called 3s, okay? And so I can understand the confusion matrix to help tell me, first of all, where the errors are, so I can decide if they are errors I can live with or not, okay? And maybe point to directions where I can fix my system to get better. Why am I having so many errors of this type? Any questions? So one example of where I thought a confusion matrix was very enlightening in a project that we did. We had a system where we wanted to try to look at a piece of text and try to tell what year it was written. Could I look at your project proposal and tell when it was written, For many of them, I think it was probably between 2 and 4 in the morning last night. But in general, we would like to be able to look at books and things like that and try to tell when they were written. So here was the result of our classifier. That would say we broke all the documents into 20-year periods, okay? And we had made a prediction. And we have a box here showing us how often on documents that were written in 1900, how often did we guess a year in the 20-year period associated with 1900? Okay, what does this what do you learn looking at this confusion matrix? Okay, the people kind of get the idea of what we're trying to do. We have text, we know when they're written. I mean, you know, in our test bed, we know when they're written. We want to try to predict when they're written. What is interesting when we, you know, what does the confusion matrix show us here? Okay. To me, it shows that the fact that I see color along the main diagonal is good, okay, because it kind of shows me that I'm getting answers right. But I noticed that the main diagonal is not necessarily, the actual main diagonal is not always the darkest box, okay? That sometimes there are mistakes that are being made. What do I see about my errors, though, that is interesting? Because
When
I
you
see my
misclassify,
errors.
you're usually close.
The errors are usually pretty close. One thing that's true about, in this case, my classes had a natural ordering to them, right? It was that they were 20-year periods, I guess generations, right? And it's showing that when I had when I called it wrong, I was often within, you know, called it in a nearby generation. That to me is kind of interesting. It's clear that I had more trouble at kind of the ends of the periods, okay? That, you know, papers that were book documents written in 1980, I had a hard time of telling, you know, I often called them 2000, okay? So I had it's clear I had problems at the boundaries. I was more accurate at the middle, okay? I claim that being able to look at a confusion matrix like that, I could tell something. Any questions? Now, when you have multi-class classification, one thing to recognize again is that the classes, the more classes you have, the harder it is to get a high accuracy classification. Okay, in this particular case, again, I had, if we say that my classes were in 20, you know, what do you call it, by 20 years, I think I had like 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like 10 or 11 classes. Okay. It should be clear that when you measure the accuracy, how often did I get the class right? Okay. This is what you call it. It's hard to get a high accuracy the more classes you have. And that can be a problem because when you're trying to evaluate a system, you want to be able to recognize when you're making progress. And if your problem is too hard, that, you know, if let's say you had 1 million classes, you know, recognizing whether you know, if you've got an accuracy of 2 out of 1 million rather than 1 out of 1 million, did you double your accuracy or is that just noise? A statistic that is usually better, okay, is to do what we would call the top K success rate, okay, where suppose, let's say, when your classifier gives a label, each label a probability or a score as to how much it thinks this label is right, okay? One possibility is that you give your classification system credit for the right answer if it fell into one of the top K guesses. Okay, if there were n possible labels, okay, if you said that this was the third best choice, if the one that was the real answer was your third best choice, if K is greater than or equal to 3, you give yourself credit for it. What's good about scoring according to this is that it makes it a lot easier to tell whether your system is making a little bit of progress, okay? Because, you know, you kind of want to select the value of K so that, you know, you're getting a decent performance. Let's say something like 50% of the time you fall in the top, rather than 1 out of a 1,000th of the time. Okay, but you know, if you have a case so that your, you know, let's say your baseline system or your first attempt scores around 50%, there's room to make the number better by improving the classifier, and it'll be recognized. Once you get your top K success rate too high, you're then better off using a smaller K. So again, you can recognize whether your system is making progress. Any questions about that? Okay, this I think is a statistic that is a useful thing to be able to do. Any questions? There are a separate set of statistics for judging how classifiers work. Okay, what you call it, the you know, the absolute error. Okay, if you have if you have a regression system, okay, the error is kind of the difference between your forecast and your observation. So the observation is presumably the real number. The F is what you are predicting. Absolute error, okay, is what you call it, the you know, the difference between what you call it, the forecast minus the observation. Relative error is the delta over the actual observation. Okay, and often the relative errors, okay, are more interesting statistics to compute. Okay, because it gives you you know, a kind of a better sense of how close you are. Any questions? In your movie thing, which would have been, when you were trying to and take it back before we get to the movie thing, it should be clear that for either one of these, the absolute error or the relative error, you can aggregate these over many tests in a couple of different ways. The mean squared error, okay, basically gives you the average value of the squares of the error, okay, be it either this or this. What is the good thing about taking the mean squared error? Why do we square it? What is the advantage of taking the mean squared error rather than the average error?
Negatives and positives won't cancel out.
Because a negative and positive will cancel out. Sometimes you hear about the mean absolute error, okay? But again, the main thing is we don't have that cancel out, okay? So typically people will talk about either using the mean squared error, or sometimes they talk about the root mean squared error by taking the square root of it, just to kind of bring it to a level that's easier to understand. Obviously, these two are kind of correlated with each other. Any questions? When you were using the movies, when you were trying to predict the movie gross, what was the error metric that was used? Does anybody remember from that assignment, if you wanted to see how good your movie gross prediction was?
It was the log square error, or the log error, excuse me.
That was the log of the error, okay? The log of which one? The absolute error or the relative error?
I don't remember.
Okay, so what does the effect of the log do? Okay, that's kind of, again, it's a question. I guess the important thing is to try to make sure that you treat errors on big things the same way you treat errors on little things. In movie grosses, if we were just thinking in terms of absolute error, you know, if you have a world where there's a few huge blockbuster movies, you know, Avenger type movies, and a large number of you know, smaller movies, the absolute error on one Avenger movie, you know, if you're talking about something that's going to make the difference between, you know, $1 billion and $1.1 billion is a huge difference in terms of absolute error. It's a really small difference in relative error. Okay. And so if you have things where the items differ in scale, aggregating the relative error is a much more sensible thing. Any questions about that? Okay, good. Okay, so those are the kind of statistics you will use for your evaluations. What is the right way to evaluate your system? Okay, now in an ideal world, typically what happens when you're doing a machine learning like thing, you are going to train on you get some data, you're going to train on some of the examples, you're going to test on some of the other examples, and there still can be kind of sins, even if you kind of randomly separate your testing and your training with some kind of discipline. The best possible training evaluation to keep you honest would be a world where you make out of sample predictions. Out of sample predictions is a world where you're evaluating your model on things that you had never seen before. So there are people who study in biology. There are these programs that have these big try to make predictions of protein structures. And they have an annual competition to decide what the best protein structure prediction program is. And this is a big deal. If you're the winner of these CASP competitions, you are, you're the world's best protein folder and the world is your oyster. But what they do is they will evaluate programs on they will have these competitions, and because they knew that if the data was out there, people would consciously or subconsciously cheat. The way that they do these things is the right answer on protein structure predictions typically involves sending a graduate student into a lab for a year's worth of experiments. And so the way that they would run these kind of competitions is they would get people with labs and they'd ask them, what structures are your graduate students currently working on? And they would tell them. And these would be the structures that they would have the competition predict on. Why? Because nobody knew the answer until the graduate student had sweated in the lab for a year. Okay? Basically they didn't have the data at the time they were training the model. Okay? And making these kind of out of sample predictions are the best, most accurate thing. But generally, we are forced that we have we may have all of our data at once. We may not get more data later. The typical issue is we take our data and we partition it into a training sample, something we train the machine learning model on. There is a testing thing, which is kind of a partition that we will use to evaluate our different methods, okay? And we keep another fraction, okay, completely in a lockbox until the end of the model, the end of the problem. And this, the evaluation data, is what we should trust to run the final model on. Typically, when you're doing your experiments, people like to only partition the data into two pieces, a testing and training. But recognize what typically happens. You take your testing data, you produce a model, You run it on your testing thing. You then say, huh, my score isn't so good. What did I do wrong? Oh, these are the ones that I did badly on. So maybe now you're going to go tune your model again, and kind of you've polluted the testing data. Okay, to really evaluate the model at the end, you want to do it on data that has never seen the light of day up until that point, because otherwise you tweak your models to get close to that. Any questions? Okay. So when you're training your model, okay, when you're evaluating models, first, again, you've got to do the partitioning into these training sets. You've got to use some statistical, metrics that we have talked about as fine things. One thing that I do find, though, is that that there are often problems that are kind of hidden when you just look at summary statistics of how your model is doing. Okay, if you have mixed your your training and your evaluation data in an unhealthy way, okay, your evaluation scores are going to be higher. And sometimes this happens because people cheat, and sometimes it happens because the evaluation data kind of contains extra copies of the training data, and it really wasn't so independent. Okay, basically evaluating the model means really kind of getting a good look at what errors you're making and trying to understand that. So when I have my students work on a problem where they are going to be doing an evaluation, the thing that I demand is that they build a kind of single command evaluation program to run it on. I'm not going to say the evaluation data. I'm going to say the test data. Okay, and produce plots of how it's doing. So an evaluation environment is kind of a program where there is an input of what the data is. There is a model that you have that's encoded on it, and that the system produces a complete suite of statistics and error distributions for when you run it. Because typically when you're in these kind of model development things, you try something, you see it doesn't work so well, you go try something again. It's important that you be able to have kind of just one command you can run so that you repeatedly evaluate it and you know really what you're kind of doing. So this is kind of my dream of an evaluation system. Okay, there is somehow some validation data. Okay, there is a place for you to stick your model in, but there are, your system should produce not only the summary statistics, but they should produce error distributions and other plots to kind of show you what you're doing right or wrong. Any questions? So one thing that I really like to see are error distributions, because often when you look at seeing where your errors are, it tells you something very, very interesting about your problem. So when I was doing my dating documents thing, okay, this is now showing me, okay, on when I had a fairly dumb baseline classifier. This is plotting what was my absolute error, okay, over how often did it occur. What do we learn? We would get an average absolute error. It's probably something like probably about 75 or something like that from this plot. What do you get when you look at this distribution? Is there anything interesting that you see in the distribution of the error from this dumb model? Okay, is this error distribution symmetric? Okay, I don't see it looking symmetric. What does it mean if it's not symmetric? That means probably if this was really a random classifier, it means that basically it turned out that they were a lot more later documents than they were early documents. So in making this kind of a call that there was going to be an imbalance there, that's one thing you kind of see here. When we built our classifier that I was more proud of, what do we see here? Certainly the error band is a lot smaller. Do I see a symmetry or an asymmetry? Maybe I see a symmetry. Okay, I'd have to see. It looks like the one bucket here is higher, but it doesn't really spread this kind of thing. I find looking at the error distribution is a helpful thing. I also find that stratifying the, the results by different kinds of test cases and looking at the error, okay, in each one tells me a lot of different things, okay? So remember, this was something about dating the text of a document. These were on different fiction documents, okay, where in this case it was 100 words, 500 words, 1,000 words, 2,000 words. These were on news documents, okay? What do we learn about my classifier by taking a look at these statistics, these breakdowns? Can one make, now that I've broken down my accuracy by these classes, okay, this shows the mean absolute error is probably the most meaningful statistic here. What actually does this breakdown tell you? Are there any lessons you get from that? Does prediction get easier as the documents get longer? Any ideas? If I look, my mean absolute error is going down as my documents get longer. It should be easier to get a sense as to how long the document is longer, so that's reassuring. But as I notice, I start hitting diminishing returns. By the time I get 2,000 words, okay, I am not getting that much better than 1,000 words. That tells me something interesting. Is it easier to predict the age of fiction documents or news documents? Any belief?
The news documents.
The news documents, again, the length saturates, but it's probably not a surprise that kind of news documents kind of have events in them that probably are more accurate to take. By stratifying my cases by topic and difficulty, I get more interesting things. Okay, any question? The last thing I think I want to talk about today is how do we build training sets when we don't have enough data, evaluation sets when we don't have data. Again, the original vision was that we take our training set of inputs, randomly partition them into training, testing, and evaluation fractions. This is hard to do when I don't have very many training examples. Okay, because again, my model gets better the more examples I train on it. I'd like to use as much data as possible for training, but how am I going to know how well my model works unless I leave enough of a chunk for a meaningful evaluation? Cross-validation is a technique where we're not going to build one model. We're going to build K different models. Okay, for purposes of evaluation. What we're going to do is take our data and perhaps break it into K different chunks, each of equal size. And what we will do is take one chunk out and hold that out for evaluation and use the other K-1 chunks for training. When we do this, what we get for a classifier we will get a accuracy or a performance on this one piece. With cross-validation, we will do this whole process k times, each time leaving one of the chunks out, and the other use the other k minus 1 chunks for for training. Okay, so now we've got not one model, but k different models, each of which we have evaluated on a sample. Okay, typically what we now get to get our real evaluation, we'd really like to know what is the accuracy distribution of the models we create. We could average the performance of these K models to get an idea, okay? But looking at the distribution of this gives us some idea of not only the accuracy of our model, but what is the variance involved, okay? What is the degree to which the performance is sensitive to the training data that we have? If we have a model that was trained on a huge amount of data, presumably, taking a little bit of the data out and retraining it isn't going to, change the performance very much. But when you have models that are trained on less data than you would like, there is often an unhappy variance in performance, okay, depending upon which bad examples got stuck in training, okay? So cross-validation is a way of amplifying small training sets, okay? And the limiting case is something called leave one out classification, validation, cross-validation. Suppose I have n different examples. One possibility is I could train n different classifiers where I leave the ith classifier leaves out the ith value, and we evaluate the performance just on one example, okay? And then the average accuracy over all of these models gives us performance. And with this, there's a way sometimes to train models with very, very little data, okay, and still get some kind of a meaningful evaluation on it. Any questions about that? Okay, any questions about this kind of a procedure? Let me see what else I want to say. What other ways can we increase small evaluation sets? Okay, this I think is often a problem. Sometimes, okay, you have a world where maybe you only have positive examples, okay? Let's say you have you only have positive examples that you've been given, okay? How can we get negative examples? Sometimes if you can sort of make an assumption that anything that was not labeled positive is negative. Okay, so let's say you wanted to build a classifier to tell who should be a president of the United States. There are 45 examples of people who were presidents of the United States. Okay, how would we find examples of people who will never be presidents of the United States that are representative? Well, one thing to know is that if you take anybody else, okay, they are probably never going to get to be president. I have come to terms with the fact that I'm never going to be president. Okay, if you have, if positive examples are rare, so if you have examples of people who have cancer, if you want examples of people without cancer, what should you do? Just pick random people. Most likely they don't have the disease that you want. Another idea is to take your real examples, okay, and perturb them. What if I go and add random noise to the features underlying some of my examples? Something that was a positive example, if I add a small amount of random noise, may create another example that is going to be similar. Maybe it takes on the same label as that. Okay, so sometimes this is a way to augment my data set by creating synthetic positive examples. Okay, and that's often a way to make this class imbalance work out better. And finally, is I would say, is a world where you make sure that you give partial credit. Again, what we would like to be able to do, if we have a good classifier, if let's say we only have 100 examples, okay, and we're having a boundary, the accuracy is how much we get, what fraction we get right. But we probably should get more credit for getting correct things that are far from the boundary, okay, rather than things that are close, okay, or sometimes vice versa. Maybe you're only interested in the tough cases, how you're doing in the tough cases. By giving credit to how close you are to the boundary, okay, that can be a way to kind of, instead of just counting right and wrong, but giving some kind of a fractional credit for this is a way you might get something more accurate. Any questions here about evaluation or anything else? I think that's all I'm going to want to say here about evaluation at this point. Okay? Any questions?